All right, hello everybody. Now we are going to look at a problem which is about combined loads. So in this case, what we have is a sign that is subject to a certain wind. The sign is also connected to a certain pole, and because of the wind, a load is applied on the sign and then as a consequence on the pole. And then basically what we have to do, we have to determine the value of the stress at 2 points that are located on a cross section on the base of the pole. So we can make a quick schematic of this. So here we have our schematic where we have that C and B are the dimensions of the sign. Then we have A is the distance between the sign and the center of the pole. Then we have D is the distance between the ground and the pole. We also have our axis Z, Y, and X. And then when we look at the cross section at the bottom of the of the pole is a tubular cross section, and then we have points A and B, which are the points where we have to determine the stress, normal and shear, depending on what kind of loads we have. So we can now move down to the list. So here we have A is the distance between the pole and the sign. Then we have B and C are the dimensions of the sign. D is the distance between the ground and the sign. And then we have the internal and external radius. Internal radius 90 millimeters, external radius 110 millimeters. And then we have the pressure that is applied on the sign because of the presence of the wind, which is 2 kilopascal, which is 2 times 10 to the power of 3 Newton over meter square. What we have to determine is basically the stress at 2 locations. In particular, we need the stress at point A and the stress at point B. So basically what we have to do, we have to go through several steps in order to obtain the solution to this problem. So the first step will be to determine the load that is actually applied on the sign, because so far we have information about the pressure that is applied on the sign, not the force. And when we make a connection, when we need to determine the stress, we need to determine the stress due to a specific load. So in this case, we have again the pressure. We assume that the pressure is uniformly distributed over the entire sign, and so it means that in order to find the load, we have to multiply the pressure by the area of the sign. So we use the formula F equal to P times B times C, because P is the pressure that is applied, and then B and C are the dimensions of the sign. So it means that this is the area of the sign, basically. So now we can go through the different steps that allows us to determine the load that is actually applied on the base of the pole. So it means that we have to basically move the load from the location, the initial location, which is the center of the sign, to the bottom of the pole. And we can do this through two steps. The first step can be to move the load from the center of the sign to the top of the pole. So we can do a quick schematic even in this case. So our force is initially placed in the center. We move the force in this direction here, and it means that if we move the load in this direction, we add a moment, and the moment is about the vertical axis. We call the vertical axis axis Z. So in this case, we will have a moment that is mz. So since we moved the load and we added the moment, we can remove the original load. So in this case, we have to calculate the intensity of this moment mz. So this moment mz is given simply by the intensity of the load multiplied by the distance between the initial location and the final location. So this distance is simply b over 2 times a. So the moment is equal to F times b over 2 plus a. When we plug all the numbers, we obtain 7.2 times 10 to the power of 3 Newton per meters. So now we have to move the load from the top of the pole to the bottom of the pole. When we move the load from the top of the pole to the bottom of the pole, we basically move it by this distance here. And we also generate a certain moment, which is about an horizontal axis. So the horizontal axis is the y-axis in this case. It means that we add a moment my. So the moment my in this case is still given by the force F multiplied by d plus c over 2. Remember, c is basically half of the height of the sign, and then d would be the distance between the bottom of the sign and the top and the bottom of the pole. So since we moved the load on the bottom of the pole, we can remove it from the top. So when we plug the numbers for my, we obtain 31.68 times 10 to the power of 3 Newton per meter. And of course, on the bottom of the pole, so on the cross section that we are analyzing, we still have the force. So now that we have all the loads that are applied at the base of the pole, we have to figure out if these loads are, if the moments are bending moment or shear moments, and if the forces are axial forces or normal forces. So when we look at the force F with respect to the cross section, we can zoom a little bit. So if this is a zoom view of the cross section, basically we have a certain force that goes in this direction here, and this is a shear force because it is transverse to the cross section. Then we have a certain moment acting in this direction, my, and this is a bending moment because it is about an axis that is on the cross section. And then we have the other moment that we called mz, which is this one. And this moment mz is a torsional moment because it acts about an axis that is perpendicular to the cross section. So this again, this moment my is a bending moment, and this moment mz is a torsional moment. So if we list, and also F is a shear force. So if we list the effect of all these moments, we have that F is a shear force. Then we have mz, that is a torsional moment. And then again, we have my, that is a bending moment. We know that each of these loads will bring a certain type of stress to our cross section. In particular, the shear force will bring a shear stress. Then we have torsional moment, we also bring a certain shear stress, and then the bending moment will bring a certain normal stress. So since we have that the shear stress is given by two different loads, we can specify. So this is, the first one is the shear stress due to the force, to the shear force. And then we have the second stress that is given to a torsional moment. Then for the normal stress, we don't need to specify because the only reason of the normal stress is the bending moment. Now we have to look at what happened in particular at the two specific points that we need to analyze. And the points that we need to analyze are point A and point B. So point A is located here. This is point A, and point B is located here. So let's start with looking at what happened at point A. So for point A, we for sure have the shear force, the shear stress due to the torsional moment, because we know that every time we have a certain torsional moment, all the points that are located on the edge of our shaft are subjected to a certain shear stress. So here I will use the blue. So this is tau torsional moment. Then we also have that at point A, we have the effect of the bending moment, because the bending moment is acting on this axis here, this horizontal axis here. So it means that the fibers that are on this side of the cross-section are subjected to a tension, and the fibers that are on this side of the cross-section are subject to a certain compression. So the other stress that we have at point A is this normal stress, which we can indicate with sigma. So what about the effect of the force? The force is a transverse force, and at point A it doesn't have any effect at all, because we know that the shear force has a quadratic distribution, and it is 0 on top and the bottom of the cross-section. So it means that the value of the shear stress due to the shear force at this point here is equal to 0, exactly like at this point here it's equal to 0. So point A has only normal stress due to bending moment and the shear stress due to the torsional moment. All right, we can look at the intensities of these stresses due to the bending moment and the torsional moment. So for the stress due to the bending moment, we have to look at the flexure formula. Flexure formula is sigma is equal to m over I multiplied by C. As we said, the normal stress is calculated through the flexure formula, and we have the flexure formula is m over I times C. So let's look at all the terms in this equation. We have that I is the moment of inertia of the entire cross-section and is given by pi. Then we have the external diameter to the power of 4 minus the internal diameter to the power of 4 divided by 64. Then we have C, which is a distance between the neutral axis and the point at which we want to determine the normal stress. In this case is the radius. So the external radius divided by 2, because basically we are looking at the distance that we have here between the neutral axis and the endpoint A. And then we have the moment, which is the bending moment, and we called it my. So we have all the information in order to determine the value of the normal stress, and then when we plug the numbers, we obtain that the normal stress is equal to 54.91 megapascal. All right, and we are done with the bending moment. We can now look at the torsion, the stress, which is the shear stress due to a certain torsional moment. In this case, we can use the formula, the torsion formula. So we have tau is equal to T over J times rho. Let's look at all the terms here. So J is the polar moment of inertia, and for a tubular cross-section, it is pi times the external diameter to the power of 4 minus the internal diameter to the power of 4 divided by 32. Then we have the term rho. Term rho is the distance between the center of the circular the circular tube and the location at which we want to determine the shear stress. Since in this case, we are looking at determining the shear stress at this location here, the distance will be the distance between the center and the edge, which is basically the radius. So here we have d over 2, the external radius divided by 2. And then we have the torque, T, which is the moment that we calculated, is the torsional moment. We called it mz. So we can plug all the numbers here. When we plug all the numbers, we obtain that the shear stress due to the torsional load is 6.24 megapascal. And we are done with point A. We can now look at what happens at point B. So we have to look at the effect of these three loads on point B. So for sure, we will have a certain shear stress due to the presence of the shear force, because in this case, point B is on the neutral axis of the cross section, and we know that the maximum stress is actually on the neutral axis. In order to find the shear stress due to the shear force, we apply the shear formula. So we have tau we have a certain tau due to the shear force. And then also we have to look at the effect of the torsional moment. So here we have this torsional moment, and we know that all the points on the edge of the cross section are influenced by this torsional moment. So here we have basically we have a double effect in terms of stress. The first one, in terms of shear stress, the first one is the tau due to the shear force. And then the second one is the stress due to the torsional moment. So we can start by looking at the effects of the torsion, because basically the effect of the torsion will be the same that we had at point A. So we have that tau is the same value because both points are located at the edge, and we know that at the edge the stress will be the same in every location of the shaft. So the stress due to the torsion we calculated before is 6.24 megapascal. Regarding the shear stress due to the shear force, we have to use the shear formula. So we have VQ over IT. Let's look at all these terms. So V is basically the shear force, and we know the shear force is equal to F. We called it F. Then we can look at I, which is the moment of inertia of the entire cross-section, and we have to use the same formula that we used before for the moment of inertia. So we have d0 to the power of 4 minus di to the power of 4 times pi and then divided by 64. Then we have Q. Q is the static moment. In this case, we have to look at the static moment of the portion of the cross-section above the area that we are analyzing. So basically, we are looking at the static moment of the portion that is above the neutral axis. And we saw this, auto-calculate this in the past, and we obtained that the static moment is equal to 2 over 3 so the external radius to the power of 3 minus the internal radius to the power of 3. Also, the last term that we have to look at is T, which is the width of the cross-section at the location at which we want to determine the stress. So we have 2 times R0 minus, the outer radius minus the inner radius. So we have all the numbers to calculate these quantities so that we obtain that the shear stress is equal to 0.7637 megapascal. So we can check the shear stress due to the torsional moment was the first one that we found, and then now we have the shear stress due to the shear force. So basically, this is how we solve this type of problems. Basically, what we have to do, we have to analyze the effect of each individual load on the points that we are interested in. In this case, for point A, we have normal stress, and we found it is 54.91 megapascal, and the shear stress, which is 6.24 megapascal. So only one component of normal stress and one component of shear stress. In this case, we have 2 components of shear stress. So basically, we have to look at the summation of these 2. So we have 6.24. So we have 6.24, 0.7637 to be consistent, 0.76. And this is the shear stress due to, again, shear force and torsional moment.